What a provoking title.
Yeah.
Very nice. Okay, welcome back, everyone. Our next session is titled Connections Between Supernova and Supernova Remnants. And Jaco is the first invited speaker, and here's our session chair. I'll just keep going. He's giving an invited talk with the very provocative title, Are the Studies of Supernova Remnants and Supernova Complementary or Contradictory? And 30 minutes.
Thank you very much. So actually, I was invited. Thank you for the invitation. And it was about supernovae and supernova remnants and the connection. Am I a specialist on that? But then he pointed out that I wrote a textbook. So I guess I'm actually a specialist on all the topics that are related to supernova. So it will be a little bit of a mix. I will stick to the topic in the beginning and later on just plug my own latest results. And now this doesn't work, so I guess I still have to do this, or it will
restart the. No.
Well, okay. Well, now nothing works. Okay, this is okay. Okay, so just start at the basics. Of course, we have the supernova classification scheme. It's mostly based on spectroscopy, also a little bit light curves. On the one hand, we have the spectroscopic classification, type 1, A, B, C, the other hand, type 2, based on the hydrogen or not. But of course, our understanding is that some are core cloud supernovae, 80% of them all, and about 20% are thermonuclear supernovae. So that is a different classification based on our understanding rather than the spectroscopy. And here you see some of the spectra that you can get for that. Yeah, it should work now. It does work. Now, our theoretical understanding is, of course, that a type 1A, a thermonuclear supernova, involves a CO white dwarf that explodes. And as a result of that, most of it, say 0.5 to 1 solar mass of the CO white dwarf will be turned into nickel 56 and iron. Whereas for core cloud supernova, you expect more oxygen. And most of that oxygen is actually built up during the latest life of the supernova. So this already suggests that if you want to identify a supernova remnant as a core collapse or a thermonuclear, you just look at the iron content. The other thing to note is that the amount of oxygen, I think this is a sort of an average over all core collapse supernovae. The oxygen content, of course, depends on the mass of the progenitor. A low mass, not that much oxygen. A high mass, a lot of oxygen. This graph is maybe a little bit old. You see that at the very highest masses, there's a discrepancy between different models. And that's basically because we don't know where the mass cut is. Is there a black hole or not? So, you have to take all this with a little bit of a grain of salt. And then the intermediate mass elements, silicon to calcium, basically they're produced by both in sort of equal quantities. Now, this idea, of course, was put into practice when we had the first imaging spectroscopy with ASCA, and Jack Hughes has this very influential paper where he showed, the mean LMC supernova remnants, and then you look at the ones that are presumably massive star supernova remnants, and you see that there is indeed a lot of oxygen near magnesium and silicon, and not so much iron. And you look at the type 1A, and you see this bump here, which is the so-called iron L bump. So many lines, and well, you can't see it here. You also have iron K at 6.7 keV, which is also indicative of a lot of iron there. That's not to say that a massive star doesn't have iron. We all have seen Martin Laming's talk, where we see that there are iron bullets in cast A. But if you look at the overall abundances, more oxygen, core collapse, iron, you're talking about type 1As. And basically, this is sort of a regraph here. I show here EL102, very famous, where you see really the neon lines. And if you look in high resolution, these are beautiful lines. Whereas you look at 0519 in the LMC, you see this iron L bump, and you can resolve them in individual lines if you have a high resolution, spectra. So we can type supernova remnants, connect them to the supernova based on the X-ray spectrum. But of course, we pick the nice samples. By now we have some secondary indicators. I think they build up over the years. We already had some hunches that type 1As look more roundish than core collapse supernova remnants. Then Laura Lopez quantified that and showed indeed that there's a dichotomy between type 1A supernova remnants and core collapse supernova remnants. The core collapse supernova remnants being more irregular. For the SMC, it's not that clear. This is what I heard from Laura. We heard a talk by Katie, who says actually it's still very clear, even for the SMC, except for EO102. But actually, that may be mass loss, right? So basically, of course, if you have a very irregular explosion and you have a very massive star, the explosion itself will be more spherical by the time the shock wave hits the outside. And if you have a very compact star, probably you preserve much better what's inside. So it may be a mass loss thing. I'm not sure how to test that, but that's at least a suggestion. Now, another indicator is if you look at type 1A supernova remnants, I think all of them basically have Balmer-dominated shocks. And for Balmer-dominated shocks, what you need is at least partially neutral surrounding. Now, one model for the single degenerates is that you have an accreting white dwarf, and you have stable accretion, and you expect a very UV bright star. And that should ionize the medium. So this scenario is basically ruled out. Now, you can get away with it if you have, say, some puffed up wind or whatever, it absorbs. But, the basic idea, we had our super soft sources. They were candidate type 1A sources. I don't think you can have them, right? So you need something in addition. And then more recently, and it was already talked about in connection to Vikram's talk, this is the iron K line, the centroids, and it looks like type 1A supernovas have centroids that are lower in energy, that's a lower ionization state, and the core collapse ones have a higher ionization state. And of course, there's some discussion there whether it's an indication, and it probably, as Carlos has shown, it relates to the circumstellar medium, the density of it. We should always be very careful. I think I have something there. We should always be very careful not to change it around. Type 1As have a tendency to have this, but it's not a single indicator. Okay, iron K line low, it must be a type 1A. You always have to be very careful. And maybe in future we can combine it only in a very quantitative method, but I don't think we are there yet. Now, so we have our maybe predators or guess hint how to identify type 1A's supernova remnants from core collapse supernova remnants. And luckily, we also got the light echoes. I think back then it caught us by surprise that these were existing. The weird thing is, Sidney van den Berg actually wrote a paper that we should be looking for these things. So that was sort of surprising. Anyway, so now finally, at least for a handful of supernova remnants, we can see what the type really was because we can get the spectrum. I don't think all of the light echoes have had spectra observed. But luckily, the obvious candidates indeed turned out to be as we thought it was. So 0509, and not only was that a type 1A, we could identify, or not me personally, but that it was a 99 T-like. So as we have heard, so a more bright event. Tycho supernova remnant was a normal type 1A, and then Cas A was indeed a supernova type 2B, which Roger Chevalier made a suggestion in 2003. I thought it was very detailed. Yes, but it bore out. So it's you would like to call it the 1993 J-like. I'm not sure if that is a good supernova lingo, but it sounds at least like it. So all's well that ends well, I would say, but of course there are some problems there. So one of the things, of course, is that we would like to know, are we dealing with supernova remnants, type 1A supernova remnants, coming from a single degenerate or double degenerate? And there things become very messy. So if you look at the supernova explosions themselves, there is very little evidence for double degenerates. People try to look at predecessors or the surviving companions. They didn't find anything. They don't find much evidence for some early interactions of the shockwave with its companion. I think there are a few candidates. So I think within the supernova community, but maybe I'm wrong there, I think people tend to say, well, most of them are double degenerates. If you look at the supernova remnant community, I think we are a little bit split. Yes, we look at the surviving companions, so that's still related to the supernova remnants, and we don't find much. Well, we heard a talk that actually there are 3 candidates. Actually, Tycho, of course, has a candidate, but all of them are disputed, and the candidate is not a certain proof that we have the surviving companion. So from the point of surviving companions, we don't have any evidence that indeed some of them are single degenerates. But if you look at the supernova remnant surroundings, and I think this is the great thing about supernova remnants, you have a better feeling of what the surroundings are, things get a little bit more complicated. So we have now a number of supernova remnants where we find indications that there was a wind before the explosion. We're talking about a few parsec within around the supernova remnant. So, for instance, there is a molecular shell around Tycho supernova remnant. And so here you see the molecular material, and here you see it's sort of a ring-like in the sense that you have something blue shifted and red shifted there. And a very famous example is Scapular Supernova Remnant. Now, Scapular Supernova Remnant is very interesting. It's a supernova remnant, of course, of 1604. It's very high above the galactic plane, 500 parsec above the galactic plane. Actually, this creates already a bit of a problem for any scenario, right? Because you have to shoot away a binary, whatever you think of DD or SD, it's binary, and you have to shoot it away with what looks like 250 kilometers a second. Now, it can be done, but it's a very special thing. Now, maybe it would be nice to have Sagittarius A star maybe involved. I think it's possible, but anyway. But then how lucky are we that the latest naked eye supernova was like that, right? So then what we see around is actually sort of a bow shock shaped thing that the supernova remnant is interacting with. There is infrared emission associated with this. So there's 500 parsec above the galactic plane. There is really high density material. So I don't think there's a way around saying, well, that can be accidental. It could be accidental in the Milky Way, in the plane, but not that high up. So actually, with my former PhD student, Alexandros Fratellis, we said, well, it probably was a symbiotic binary that exploded, and we should be looking for the surviving companion. And then Wolfgang looked at it and no surviving companion. That leaves, we would like to have a little bit of a mixture. So this core degenerate, basically, you have a merge. You have 2 white dwarfs, and one of the white dwarfs just, became a white dwarf 150,000 years ago, and then you have so that could work. Making them all like that, I think, is difficult, right? So this is the problem. So maybe Kepler is unique. But we have also heard about N103b, that there is something there. So it's a complicated picture. So I'm wondering what this is telling. So it's not so much contradictory, it's more puzzling. But then I didn't have to see. Then there is a very special case of RCW86. Actually, one of my favorite supernova remnants because I worked on it as a PhD student. It's rather large. It's 40 arc minutes. It has a rather thin shell, and it has the largest contrast in density and velocity that I know of. So here you see X-ray signaton emission, and here, for instance, the measurements indicate a shock velocity of around 3,000 kilometers a second. And in these very dense parts, there is a velocity measured of around 200 kilometers a second. And the reason is probably that we have a cavity. So basically, you create a wind bubble. The supernova remnant goes off. It's maybe a lopsided bubble. So in some regions, you are inside the shell, the thick shell, and the shock velocity rapidly drops. And in another region, it's still relatively high. So that gives you all the answers that we want to have. One puzzling factor is there. If the X-ray spectrum is more like interstellar medium material, plus a lot of singleton emission, but you do find this weird iron K line at 6.4 keV, which is rather neutral. Now, the only way you can have the iron K stick out above the non-thermal emission if you have a lot of iron. So this is basically one of the indications that we are dealing here with a type 1A supernova and rather than a corporate supernova. I'm not totally convinced. I come from a time that I still believed Westlands thinking that there was no B association there. Actually, I had a bachelor student look at it with Gaia, and there doesn't seem to be much there. So I think all indications are it's a type 1A. But if that's true, how do you create with a progenitor at such a large cavity? When we talk about Kepler and Tycho, we are talking maybe about an 8 HGB wind. But here you need really a fast wind that doesn't leave much of a trace. So you need a lot of energy, but with very little mass. So then you're thinking more about a disk wind or something like that, something that goes with 1,000 kilometers per second. So it's a little bit old. So we're hoping at some point maybe to get a light echo, but it's maybe a little bit too old to really get something. So these are all, not only that for some supernova remnants, we do find evidence for a wind, we find evidence maybe there's a variety in sort of wind mechanisms there. This is rather large, so it's difficult to really search for a surviving companion, but I think Wolfgang has had a try at it. Now then, about subtyping supernova. We already know now that 0509 was a 91T based on the supernova light echo spectrum. Now, if you look at supernova 1006, which is a famous type 1A supernova remnants, basically the typing there was not based on the iron content, but more on the fact that it's so high above the galactic plane, and maybe also that it has neutral hydrogen around it. If you look at the exospectrum, you see a lot of oxygen. Actually, I did some investigation of this bright knot here, and it looked like an ejecta bullet with oxygen. If you look at the iron content, there is iron, and it's, the ionization state is rather low. So you see iron at 6.4 keV, which was discovered relatively late, but there doesn't seem to be an awful lot of iron. And actually, there's a star behind it, a UV bright star, and they look in the absorption. And they see that I think the reverse shock is still in the silicon-rich layer, not so much in the iron-rich layer. And there seems to be, from the iron that they see, there seems to be a lack of iron. So, if at all, I think this is a sort of an iron-poor type 1A supernova. But of course, we need to quantify that a little bit better, right? It was at 0.2 solar masses or 0.1 or maybe still 0.5. You can play around a little bit with the dynamics there. Then we look at Tycho. It has this iron L bond, but it's not very prominent. But I think we can explain everything here just by the dynamics. And Carlos has run some models, so everything is consistent with the normal type 1A, which is also, of course, consistent with the type 1A light echo spectrum. So no issues there. Then we go to Kepler Supernova, and we see that it has this very huge iron L bump, a very prominent iron K line. So it seems to be very iron dominant. So in this case, we have a lot of oxygen, and here it's very difficult to find any oxygen related to the ejecta at all. So it seems to be oxygen poor, and this is an oxygen rich in terms of the ejecta. Now, because there's so much iron there, of course, it's sort of natural to say, well, maybe it was a 1991T light. First of all, there was some, it was not quite clear how far away Kepler Supernova was. There were estimates at 3 kiloparsec up to 9 kiloparsec at some point. And we didn't find initially the gamma ray emission, and then there were some models that said, well, then it must be more than 6 kiloparsec, so that made it also a little bit more energetic. It's very iron dominated, so it was thought, or at least suggested, that this might be also a 1T supernova explosion. But not so fast. If you look at the historical light curve, and we have in black here European data and in red the Korean data, and we compare it to light curves of known supernovae, we actually see that the peak is relatively narrow. So if we compare it to the 91T1, so this is in red, you see it's much broader. So of course the peak you don't know, because we don't know really the distance, but the width of course is an indication whether it's a very bright one, a 91T-like, or a more normal one. And actually, the light curve is a reasonably normal one. So not only that Tycho supernova remnant may come from a normal type 1a, it looks like also Kepler's supernova remnant comes from a normal type 1a. And that's a little bit surprising. So apparently, being normal still has some diversity, and the societal impact of that you can think about for yourself. Now, if you look at this, actually, I normalize this was from a review. I normalize everything for comparison to 5 kiloparsec. Pilar Luis Lafuente did actually the stretching method, and she came out with the same distance, and at around the same time, Ravi and Tweet did a measurement combining Doppler shift with proper motions, and also came out with 5 kiloparsec. So it looks really like it is at 5 kiloparsec, maybe plus or minus 0.5, I would say. So it seems to be consistent. So anyway, this implication I already explained to you. Now, another indication that is sort of a hot topic since the last 10 years or so is that we have now enough statistics to really see the manganese and the chromium lines. Okay. And maybe the most famous example is 3C397. It's a little bit of a weird supernova remnant from that point of view. I'm not sure what Laura thinks about this. You could argue it's a little bit older, so it is maybe all the remnants can be different. But if it is very boxy, it probably means that the circumstantial medium is very weird, right? And that could be a coincidence. It happened to be near something weird, but how many coincidences do you want to have? Now, the manganese to chromium, so the manganese, and Ivan may correct me if I'm wrong, or Carlos, so it comes about because you have a neutron-rich element there. Now, one way to get a neutron-rich element is it was there all the time. And basically, you work yourself up from the nitrogen abundance to whatever happens there. And of course, the nitrogen abundance was there all the time, and that's what we call metallicity, right? Or you could have maybe some processes like simmering in the inside or during the explosion that makes the material rich. But in order to have that, you need a very dense white dwarf progenitor. So the suggestion is now here that in this supernova has come from a Chandrasekhar mass explosion. It has this weird morphology. If I would see this, I would say, well, likely it's a core collapse supernova. But if you look at these things and the iron content and the magnesium, you say it's a type 1a. So it may tell us something. Now, we had the talk by Vikram about W49b. It's actually the same thing there. If you look at this weird thing, you say, well, that must be a core collapse supernova, and it seems to be in a high density environment. It's also a little bit boxy, certainly. If you look at the infrared, it is a much more boxy shape. There was a suggestion maybe of a jet here. So there was a suggestion maybe it was even a gamma ray burst remnant or some hypernova remnant or whatever. That idea has gone away. But the spectrum is really, really weird because it's highly absorbed, so we can't see anything about the oxygen. But it has this very bright iron K line. And indeed, if you do the analysis, you also see that there is again manganese and chromium. And the ratio is maybe not as high as 397, but it's really almost up there. So I think not only the iron indicates a type 1a, but also the manganese indicates a type 1a. But if this is true, why do we have a type 1a of a Chandrasekhar mass very close to molecular cloud? Is it again a coincidence or not? I think the highest manganese content are in two weird niche-shaped supernovae. So, it's a small number statistics, but it is maybe an indication of something is happening there. And now for something completely different. So as I said, I would also plug my latest results, and it is connected, of course, to the progenitor theme that runs in here. It's not directly connected to the supernova, but I did want to say a little bit about the dynamics and the circumstellar medium of test A. After all, this is officially now the test A here, right? We have so many nice observations we can say that we have to pay attention to it. As I said, it's a type 2b, so it's strip star, a little tiny layer of hydrogen left at the moment of the explosion. We heard Martin Lamek's talk that we have an ejector mass of around 2 to 4 solar masses, so it must have been a very stripped star. And it's been a lot of talk, do you need a binary for that or not? I think most people agree that you need a binary to lose that much mass. And I will poke a little bit at that without any firm conclusions. Now, it's evolving in a high density environment, and the current CSM density at the shock front is around 1 to 2 particles per cube centimeter. And that's indicative of a red supergiant wind. So if you have a Wolverine A star wind, you have a very low density because the velocity is there. Now the abundance factor. So this is basically what we expect from a core club supernova remnant. As I told you, lots of oxygen and neon and magnesium. Well, in case we do have a lot of oxygen, but there's not as much neon and magnesium. So actually, this is from the iron bullet. So here again, you see the iron L complex, some iron K. But if you look at the other knots, what you see is it's a lot of silicon and very little neon and magnesium. So it looks like neon and magnesium are underabundant by a factor of 0.1 with respect to the core collapse supernova remnant bottles. There's a lot of oxygen because it's so oxygen-rich supernova remnant. So for oxygen, there's not a problem, but there is a problem for the neon magnesium content. Actually, also in the optical, it's very difficult to find neon. I think Rob has one paper that during one little flare or so, he did see some neon and was very excited about it. And we've seen actually also neon in forbidden lights in the infrared. It's a clearly bipolar explosion, so the shock wave is rather roundish. So that tells you that the CSM, I will say that there's a variation there, but it's not that different. Every shock wave has a tendency to become more spherical in a uniform density. But if you look at the composition, what you see is actually there is a lot of intermediate mass elements in the jet direction. So there's a jet in this direction, and there is also a counter jet which is less well developed. So maybe there is a difference in where the jet is going through. And if you look more in the equatorial region, you see more of the oxygen-rich optical ejecta, but that's also true, in fact, if you look at the the silicon content. Actually, one way to make a jet image in X-rays is you divide a silicon image by a magnesium image. So there's a lack of magnesium in this direction, and that's a little bit of a proxy of oxygen. Oxygen is difficult in X-ray because of the high absorption, as you can see here. So there's some oxygen here, but the absorption is so high that it's more difficult to really probe that. Now, about the latest result that I had. So this is about the expansion of X-ray, and what we looked at is actually the continuum. And the reason is that most of the continuum here is X-ray singleton radiation, and it really traces the shock fault rather than the ejecta. Now, there may be some contamination. This is the basic idea here, and it was recently published by me and both Dan Norton and Castro. So what we did is actually we divided the remnants in sectors, focusing on the forward shock and where we think the reverse shock is. And we have an idea where the reverse shock is based on the radio absorption data. And what is already done for some time is that the reverse shock seems to be a little bit shifted towards the west. So they're not concentric. In addition, actually, I also measured the X-ray expansion of the jet. And here you see a difference image. And what we found is actually, well, the forward shock is going very fast. We already knew that from previous results. It's around 5,000 to 6,000 kilometers a second with some variation there. But if you look at the reverse shock, it's going outward in this part of the remnant, and it's going inward in this part of the remnant. So the reverse shock, despite its name, mostly it goes outwards, at least in the early phase. It's only if something special happens that it goes inward, or when the supernova is relatively old. The expansion parameter of the outward shock is actually around 0.6 to, in some cases, even 0.9. On average, around 0.7, which is consistent with an evolution in a dense 1/r². So the surprising thing that's going back into the west. Now, one of the things that you can do is, of course, you have a distance, so you can change the proper motion into a shock velocity. As I said, the outward shock is around 5,000, 6,000 kilometers a second. The reverse shock is going inward, so you get a negative velocity there. But of course, what matters for the physical shock velocity is the combination of the ejected going outward and the reverse coming backwards. Now, if you take that into account and you just use a little bit of geometry and the free expansion velocity, what you see is this dashed line, and what you see is that the shock velocity itself, the physical shock velocity, is around 2,000 kilometers a second around. So the difference between the reverse shock velocity and the ejector speed, and then it really climbs up even up to 8,000 kilometers a second. Now we know from theory that X-ray singleton emission really requires something like 3,000 kilometers a second and up. Otherwise, you don't accelerate fast enough to offset the singleton losses. And this seems to bear out. So when we look at the morphology of Cat A, it really looks like in the west we have this X-ray singleton emission and a reverse shock, and basically that coincides with velocities about 3,000 kilometers a second. I'm almost done. Now, the other thing that we could do, because we combined actually all, I think, 19 observations of Cat A, and in one go, and it even fit a deceleration or acceleration. I didn't expect much from that because actually it's rather low. But what I found is actually you do find deceleration and acceleration. So it looks like the eastern part is actually decelerating, but decelerating too much with respect to the models. And the west is actually accelerating. And this is a little bit weird, right? I'm talking here about the forward shock, because you would think, okay, maybe the forward shock bounced into something, and then the reverse shock started moving back, but you should have a deceleration there. So I wasn't quite sure about the interpretation of what it meant to have a reverse shock coming back. Now, there are a number of ideas there. First of all, when does the reverse shock start coming back? And you can make this criterion here, which you can find actually in my book. So once the ejecta density is smaller than the circumstellar medium density, basically the reverse shock starts moving backward. So one way would be to have a hole in the ejecta. And actually we could have holes like that, right? We have the rings, and inside the ring, maybe inside the ring is going back. So that was one idea that I had. Then around the same time I was working on the paper, Salvatore came to me and said, well, I already showed some preliminary results. We tried to model that, and we came up with this one-sided shell. And so what happens is, if you have this shell, suddenly you get a deceleration of the forward shock, you build up pressure, and it drives back the reverse shock. But once the forward shock is going through the shell, it picks up speed again, it accelerates. So the acceleration could be a result of that. So it is a past encounter with a shell. And basically, so for most of the supernova, and the reverse shock is still going outward, but in this one side, it's going backward. And this is what Cat A should look like in 500 years or so from now. This whole asymmetry seems to also be there, actually, if you look in the optical knots. So there is a difference between the front side and the back side is probably related to this. Another idea that came to me when I started reading a paper I was actually a co-author on a long time ago, and I'd forgotten about, is that we were working with a graduate student, Bob van Velen and Norbert Langer, and Norbert Langer at the time had always the idea Cas A progenitor was a Wolf-Rayet star, and he wanted to test it with simulations. So we came up with some models with a Wolf-Rayet star phase that lasted from, say, 5,000 years to 15,000 years. And then you have, we discounted this because basically, in the paper we said, well, the reverse shock should be coming backward if you have a Wolf-Rayet star phase. And it's not, so we discounted the Wolf-Rayet star phase. But now it's a little bit back. So in principle, what you could also have is a very late Wolf-Rayet star phase with a sort of a lopsided bubble. So if you do that, and the question is, how do you get a lopsided bubble? But if you do that, in principle, you can also explain this. So that's an interesting idea. So maybe in the last phase of its life, it did have a fast wind with a sort of a bubble around it.
Yeah. So we're telling you that it's time to wrap up.
One thing that you might be interested in is, do we need the binary or not? Now, Rob Thiessen has some, or not Rob Thiessen, it's PhD student, Catherine Weil, found H alpha emission around Cat A, and they suggest that Cat A is interacting still with this dense material from the Suppression supergiant. Now you can calculate based on the current density and shock from what the mass velocity rate, or actually the mass velocity rate of the wind velocity is, and you can calculate how much mass in the red supergiant phase is there. And it's around 18 solar masses, depending on what is the maximum velocity. So you don't need something catastrophic, right? It could be that a binary sort of forces a slow evolution of a red supergiant wind, that's fine. The idea that maybe you have a first supernova removing all the mass, and then later on Cat A exploded, I think it's sort of excluded by this. Okay, that was it. Thank you.
Wasn't gonna stop you because I was on most of those papers.
It's very good. Yeah, you need friends. Yeah.
We don't have, I'm gonna let Dan take over, but we don't have any questions. But I know that there's gonna be a ton of questions about this, and I have about 20 myself, and Rob has a question, so, maybe we,
Pivot to the next.
yeah, so go ahead.
Yeah, sorry. Yeah, well, thank you very much. And
Okay.
you've had so much, means there's a lot of questions that we want to have, and we'll address this either in discussion, and I'll leave time during the summary talk at the end, so for the reason for everybody to stick around.
Hi, Maria. You can start sharing your slides and you can unmute yourself.
All right, yes, Maria is next.
Yes, can you?
Wonderful.
I heard you for a moment, but then you went out.
Now?
That's good. No slides though.
Yes. The volume is going down.
Your audio is going in and out.
Yes, I see. I can see it in my settings for some reason. Can you hear me?
I would maybe suggest turn off background suppression if you have that on. It might be.
To do what?
Do you have background suppression on?
Yes.
Maybe you need to turn it off.
Now maybe it's better.
That's better now.
Yeah, and talking closer helps as well.
Okay. So I will start sharing my screen.
Yes, please. Thank you.
Wonderful. Maria, remember, this is 15 minutes total, so aim for 12, okay? I'll interrupt you if you start going too long.
Okay. So hello all. Thank you for giving me the opportunity to present my work in this meeting. I'm Maria Kopsachili, and on September 1st, I'm starting my first postdoc as a fellow at the Institute of Space Sciences in Barcelona. However, what I will talk about is mainly part of my PhD at the University of Crete, and this is multi-wavelength study of supernova remnant populations in nearby galaxies. This is the outline of my talk. First, I will talk about supernova remnant populations in nearby galaxies. I will present the luminosity functions, and I will focus on the galaxy NGC 7793. I will talk about X-ray supernova remnants in this galaxy, and I will introduce some diagnostics for the optical identification of supernova remnants. Then I will say a few words about my future plans. So in order to identify supernova remnants in nearby galaxies, we have followed an automated method. I use this extractor in order to detect point-like sources. From the detected sources, I have kept those that have H alpha 3 sigma above the background. And from those, the sources that present self-worth over H alpha ratio higher than 0.4. And according to the traditional diagnostic, these sources can be considered as supernova remnants. Then I created two samples, a more secure one, for which the self-worth over H alpha ratio is 3 sigma above the 0.4 threshold, and the less secure one, for which this ratio is between 2 and 3 sigma above the 0.4 threshold. And finally, I inspected our sources. In total, we have found 42 supernova remnants for the more secure sample and 54 for the less secure. And these are for the galaxies that you can see here. And the next step was to calculate the incompleteness of supernova remnants for those galaxies as function of H alpha and self-worth 2 luminosity. However, the incompleteness is affected also by the background of the galaxies. So what we did was to split every galaxy in 4 regions depending on their background, and to calculate the incompleteness in each of these regions. Then we constructed the incompleteness maps that you can see here. The blue squares show the completeness as function of the H-alpha and L42 luminosity. Different panels are for the different background ranges. The circles and the squares show the candidate supernova remnants of the more secure and the less secure sample, respectively. So the next step was to calculate the completeness corrected H-alpha and the joint L42 H-alpha luminosity functions. So here on the left, the hatched histogram shows the H-alpha luminosity distribution of the candidate supernova remnants. We correct for the incompleteness and we obtain the gray histogram, which is best fitted by skewed Gaussian. This is the function that describes the skewed Gaussian, and these are the best fit parameters. So this is the H-alpha luminosity function. Now, in order to construct the joint L42 H-alpha luminosity function, first we put our sources on the H-alpha L42 plane, and we found the best fit line along which we'll present the luminosity function. In order to find the width of the luminosity function, we calculated the distance from each point to this line, but on the L42 axis, as you can see here. And the distribution of these distances is described by truncated Gaussian. And then this gives us the width of the luminosity function. And in order to find the profile of the 2D luminosity function, we have projected these points on this line. And we find that, again, their distribution is described by a skewed Gaussian with these best fit parameters. And putting all together, we obtain the joint L42 H-alpha luminosity function, where here along the L42 axis, we see the truncated Gaussian, the width, and here the skewed Gaussian, and this is the best fit line, actually. So what we did in this project was to follow an automated method for the identification of supernova remnants, which allowed us the calculation and the correction for the completeness effects. And this is important because now we can compare between studies of different sensitivities and also between studies and models. In addition, once we have a large sample free of selection effects, we can have a more accurate relation between supernova remnants and star formation rate. I focus on NGC 7793 because this presents the majority of the supernova remnants among the 4 galaxies that I showed earlier. Because also there are Chandra data available, and some of its regions have been covered by IFU observations. And although this galaxy has been studied in the past in X-rays, very detailed, for example, Panuti et al. Have done a very nice work, including supernova remnants. And now, because we have a larger sample of optical supernova remnants from the work that I presented you earlier, we can have broader correlations between X-rays and optical supernova remnants. So on the left, we can see a composite X-ray optical image of the galaxy. And all the circles show the X-ray detected sources. The orange ones are the X-ray detected sources that coincide with optical supernova remnants from our previous study. And if we put all the sources on a hardness ratio diagram, we'll see that the orange ones fall in the softer part of the diagram. So what we can say for now is that we have at least 5 new X-ray supernova remnants with optical counterparts. And some of them have also radio counterparts. What is very nice here is that there are some IFU data for this galaxy, and some of them are in the region of the supernova remnants that I showed you earlier. And this is very important, not only because we can have more information on the supernova remnants as individual objects. For example, here you can see that we have directly their spectra, but also because we can have information on their environment, which is very important if we want to explore feedback processes. which is what we want to do in this project. Speaking of high-view data, I have to say that they can be very useful in the process of identifying supernova remnants using multi-wavelength diagnostics. As I mentioned earlier, the most traditional diagnostic for the optical identification of supernova remnants is the self-orthoverage alpha ratio. Sources with this ratio higher than 0.4 can be considered as supernova remnants. This is an empirical tool that seems to efficiently differentiate shock-excited from photoionized sources. But let's take a look at the plot on the left. The red histogram shows the distribution of the photonization models and the green one of the shock models from mappings 3. These correspond to H2 regions and supernova remnants respectively. And this is the 0.4 line. As we can see, indeed, there is very little contamination for ratios higher than 0.4. However, we miss a significant fraction of shock models that correspond to low excitation supernova remnants. So this led us to explore more diagnostics, which are more efficient in also low excitation supernova remnants and include 2 or 3 emission line ratios at the same time. In other words, we're talking about 2 and 3 dimensional diagnostics. And in order to construct them, we have used shock and photonization models from mappings 3 that are characterized by a relatively wide range of physical parameters, and also support vector machine for the construction of the curve or of the surface, in the case of 3D, that best separate supernova remnants from H2 regions. And here I present some of our diagnostics. In all cases, the green color corresponds to supernova remnants, while the red to H2 regions. In the first line, we have some of our 2D diagnostics. The black line is the separating line, while on the bottom, we see some of the 3D diagnostics where the blue surface is a separating surface. In all cases, the lines and the surfaces are described by a function where X, Y, Z are the emission line ratios of the diagnostic. So for each detected object, when this value is higher than 0, it can be considered a supernova remnant. These diagnostics can recover up to 33 or 35% of the supernova remnants that we miss when using the self-orthoverage alpha criterion. And this is very important, not only because now we have larger samples of supernova remnants, but also because we have different populations. For example, we have low and high excitation supernova remnants at the same time. And in order to make these diagnostics more realistic, in the future, we want to take into account supernova remnants that evolve within H2 regions. So this was my talk, and I will say a few words about my future plans. Most of my time here in Barcelona, I want to use high-view data along with the new diagnostics in order to optically identify supernova remnants, and also will explore their environments, for example, by constructing density and temperature maps, and by exploring their X-ray properties. In addition, I will create multi-wavelength observational and theoretical luminosity functions. I already saw some observational luminosity functions, the H alpha and the joint self-ortho H alpha. I want now to expand in more dimensions, in more emission line ratios. And unfortunately, I didn't have the time to talk about theoretical luminosity functions, which is a project I worked on recently. In a few words, what I did was to construct the theoretical H alpha and the 2D self-ortho H alpha luminosity functions by using shock models in an attempt to develop the basis for population synthesis models. And one of the interesting things that we found is that despite the simplicity of the method that we followed, there is a very...
Maria, we lost you.
Can you hear me? Yeah. So, yes. I don't know if there are any questions.
Wait, Maria, that was Abadani, can you just repeat the last couple of sentences? You faded out. We want to go out with a bang.
Okay. Okay. So I guess in this slide.
Just the last sentence, please.
Yeah, that
You speak
actually
ahead of
what
time.
we did, yes, was to construct theoretical luminosity functions using shock models, pH alpha and the 2D Selford 2H alpha, and in an attempt to set the basis for population synthesis models. And one of the things and the interesting things that we found is that despite the simplicity of the method that we followed, we find very good agreement between observational and theoretical luminosity functions.
Wonderful. Okay, let's thank Maria. Open the floor to any questions. Maria, very nice to see progress since I last saw you in Greece. And I remember then, and I'm seeing your plots again, I think I made the comment that she's bringing the search of extragalactic remnants to the 21st century with her approaches using machine learning and such. So
Thank
this
you.
is wonderful. Is there any points of questions? If not, because we're already behind schedule. Thank you again, Maria, and we will
Thank
move
you.
to the next
Thank you.
speaker. And I apologize in advance for mispronunciations. Is it Lei Sun or Lee Sun?
I don't see Layson on the Slack, on the chat, so let me
Okay.
actually get them, make sure they're not in the other, there they are. Sorry, Lay, I remember telling you I was gonna bring you over, but I didn't. Okay, you should be able to share your slides and speak.
Yeah, can you hear me?
Yes.
Yes, we can hear you. That's a
Yeah,
great
that's great.
background. You, screenshot. We are good.
Okay. Okay, so can you hear? Can you see my
Yes.
slides? Yeah.
Yeah.
Great. Hello, everyone. I'm Lei Sun from Nanjing University. So in this talk, I'd like to share with you our recent work on the X-ray emission of 1987A. And I here I list my major collaborators. So I believe all of you are already quite familiar with 1987A, so I will just quickly go through this introduction part. And also no need to further address the importance of 87A as the nearest supernova observed since Kepler and all of these historical supernovae. And it is also unique since we have good knowledge about the progenitor star and the explosion type. And for supernova remnant study, it is also especially important since we are actually seeing this burst of a remnant. And for now, over 30 years has passed since the explosion, and the blast wave had already encountered and interacted with the CSM, especially the dense equatorial ring as the bright ring structure here. And recently, some studies have revealed some new features on 87A, which indicate the remnant has now entering a new evolution stage. Firstly, from the simulation results, the three-dimensional MHD simulations has successfully reproduced most of the X-ray features, such as the light curves, the morphology, and even the spectrum. And the simulation also indicates the remnant will enter a new phase at around 32 to 34 years, in which the emission will dominate by the ejector material. And from the optical observations, people have revealed some new features outside of the equatorial ring, which may be related to the high latitude materials. And also in the gamma ray band, people find some enhancement of the GeV emission from the 87A region. So all of these new results motivated us to look into the recent X-ray observations and to complete the X-ray view of the remnant. So in this study, we use the Newton data. Newton has been monitoring 87A since 2007. And for now, we have already 14 observations in total, basically one observation per year. And we use both the RGS and FPN data. By using RGS, we have a very high energy resolution in the soft band. And with FPN, we got a full energy coverage until 10 keV. So the first thing we may do is to fit the spectrum by using a simple two temperature component model as commonly used by previous studies. And this model can basically fit the spectrum and give us the flux, the temperatures, ionization parameters, and also emission matters of the components. Firstly, if we see this flux, we find that the soft band flux started to decrease recently, but the hard band flux is still increasing. And the temperatures of these two components, the lower one is around 0.6 keV, and the higher one is around 2.5 keV. And they didn't change much in the past few years. But if we look at the emission matter here, we find the low temperature component decreased recently, and the high temperature component is still going up. So this is also corresponding to this change in the flux. So this two component model can basically fit spectrum. Maybe too simple, but the good part is we can try to interpret the physical origin of the two components. So here, if we look at the structure of the CSM, we know there is a equatorial ring, and from the early optical observations, we know at least there are two major components. One is the dense clumps, has a density over 10 to the 4 per cc, and also an interclump gas with a lower density around a few thousand. And surrounding this ring, we have a H2 region with a lower density around a few hundred. So if we compare this physical picture with our spectral fitting results, we interpret the low temperature plasma basically from the equatorial ring, not from the dense clumps, but interclumps gas. And we interpret the high temperature components mainly coming from the H2 region. So keep this in mind. If we look back to the change in the emission matter, it actually indicates the shock had already left the equatorial ring, but still propagating into the surrounding gas. Okay, so this 2T model can basically fit the spectrum and already gave us many valuable information, but here we see that this 2T model actually failed to reproduce the iron K line. So we see significant residue around our iron K. So here we took a deeper look into the iron K line. We measured the flux and the centroid energy of iron K, and we find that we need a third component to fit iron K. So this three component model can fit the spectrum better, especially for iron K, and the iron K is coming from the even hotter component with temperature of around 3 keV. But we also find the other two lower temperature components, the temperatures are different from the 2T model results. And if we look at the centroid energy, we find a recent decrease of the centroid energy. And this may be related to the newly shocked injector material. And this also indicated by the simulation results. So at the beginning, when the emission still dominated by the ring, the average ionization state of iron is high. And as the ejector taken over, the average ionization state of iron going down. So we may see this decrease in the centroid energy. Okay, so far we have tried firstly using a 2T model to fit spectrum is okay, and we find we need a third model to a third temperature model to fit iron K line. But the question is still how to interpret this additional component. It can be from the ejector, or it can be also from the reflected shocked gas. So what if we keep adding even more components here, maybe 4, even 5? And actually, we know this temperature should have some kind of continuous distribution. So what if we actually build a continuous temperature model and to fit the spectrum? But the question still is how to interpret the results, because you want to put everything into your model, but it's very hard to explain everything. But in this case, we are lucky because we have these simulation results which can reproduce most of the actually features. And the simulation results naturally provide us with a continuous distribution of the emission matter in this temperature versus NET space. So we can directly compare the observation result with these simulations. So how do we get this distribution? So basically we can use the differential emission matter analysis method, but I will not go into the details. But people have already made some attempts to do this, such as Jacob et al. Using the Chandra data and Alp et al. Using the RGS plus New Star data. But the result here is not consistent with each other, but also not consistent with the simulations. So here we are going to apply this method to the X-Newton data. So firstly, we do some tests. We apply this method to the simulated X-Newton spectrum by using 3 different test models containing 1, 2, and 3 different temperature components. And we see here this method can perfectly distinguish and separate these 1, 2, and 3 components. So this method actually worked very well with the X-Newton data. And if there are actually individual 2, 3 components, we can actually distinguish them. But when we apply this method to the real data, we got this. We see only 1 major peak here, plus a tail to the higher temperature end. And this peak is around 0.5 to 1 keV, and it's slowly going up. So the average temperature is actually going up. And if we pick up 3 from them and compare with the simulation results, we see the observations and simulations consistent with each other very well. And especially for these recent observations, we find a small peak here at the high temperature range. And we also see this feature in the simulations, which is coming from ejector. So the result here may show you an example in how to get this distribution and how to compare it with the simulation results and how to interpret the results. Okay, and my last part is actually about the PWN, but I will just skip this part and recommend you to refer to the talk by Emmanuela. So that's all of my talk, and I will leave this summary here and take questions. Thank you.
Okay, thank you very much. Like, there's time for questions. Is there anything on the chat immediately? Yes.
I'm surprised that you'd be getting X-rays from the rings, and it seems like it should be rated on a pretty short time scale. Is it actually heated to X-ray emitting temperatures in your simulation?
Sorry, did you hear that?
Not really.
Yeah. Do you want to repeat it a little bit louder?
Is the equatorial ring, is that actually heated to X-ray emitting temperatures in your simulation?
You mean the temperature I got from this fitting
He's
compared to
asking
the
about the
simulations?
ring. Yeah, he's asking about the ring and if it gets to X-ray emitting temperatures.
Yeah, I believe this the major peak is from the ring. Also, this tail to the higher temperature, maybe from the ejector also.
That address?
I think, the ring is not uniform in density, so I think that the shock point is depending on lower.
Yes, of course.
Any other questions? No? Okay, again, thank you very much, Larry.
Thank you.
Thanks again. All right. Now, Aravand Ravi from University of Texas at Arlington. Here in person.
Do you have a microphone? If you do, it's right here.
Seems that it's nice to- yeah.
Hello, everyone. Thank you to the organizers for allowing me to speak about my research. A lot of what I'll be presenting is sort of complementary to the talk you just heard before, which is the latest evolution of the X-ray remnant of supernova 1978. But I hope to present a little bit more using the speciality of Chandra, which is its excellent spatial resolution. So I would like to thank all my collaborators for their support throughout this project. So one of the pressing questions in astrophysics is to understand how a supernova evolves into a supernova remnant. And that's where 87A comes in. It's the closest observed supernova in several centuries, and that has enabled over 3 decades of multi-wavelength monitoring to see the birth and evolution of a young supernova remnant. And X-ray observations are particularly important because they directly track the forward and reverse shock, giving more information about the important parameters of supernova remnant evolution, like circumstellar densities, the morphology of the remnant, and ejecta kinematics. So a new phase in the evolution of the remnant of 87A has been reported across several wavelengths, and we have seen several indications that the blast wave has moved past the equatorial ring, the dense equatorial ring, and has started to heat up the circumstellar material outside, which is possibly from the stellar winds of the progenitor. So Chandra is the only telescope at X-ray wavelengths which can resolve the structure, clearly resolve the structure in supernova 1987A, which has a diameter size of about only 1.6 to 2 arcseconds. And we have been observing 87A for the past 23 years. From the first observation was in 1999. So we have a comprehensive set of observations, about 43 as of October 2021. And the latest upcoming observation is next month, and we are always excited about new observations of 87A. I have here presented some of the papers that have talked about the results from these papers, from these observations. So this is part of the Chandra monitoring program. Along with these monitoring programs, we also propose for several deep or high resolution spectroscopy observations using the ratings on Chandra, and we have 5 of them between 2004 and 2018. So my research started in 2018 with this wonderful data of high resolution spectra from Chandra ratings, and this is from March of 2018, and we obtained this spectra as a continuation of our deep spectral monitoring. And we see several strong helium alpha line and alpha lines from elements like silicon, magnesium, and neon. As discussed in previous talks, we fit the broadband spectrum with 2-component plane parallel shock models out of equilibrium. And we find that we fit them simultaneously between 2004 and 2018, and we find that a very good fit is obtained with just 2 components. And we also reprocessed and reanalyzed all the previous deep spectra, which have been published in these several papers, to consistently track the spectral evolutions. So our main aim was to study how the X-ray emitting gas changes over 2004 to 2018. So 2004 is when the blast wave started to interact with the main body of the equatorial ring, and 2018 is when we have these indications that the blast wave is moving out. So what has changed? So I'll discuss some of the plasma parameters that we from our website models. So we find electron temperatures increase in both 0.5 to 2 keV and 3 to 8 keV, and that is consistent with a scenario where the blast wave is now interacting with CSM that has lesser density than it had between 2004 and 11. So you see all these in the soft component, the data points are clumped together, but in 2018, clearly there's something which has gone up. And on the other hand, with the hard component, the trend has reversed. Similarly, because of the increasing strength in the Lyman alpha lines that I showed in the broadband spectrum, the helium alpha to Lyman alpha line fluxes have drastically reduced since 2011, and such a reduction is consistent with the changing electron temperatures. Most importantly, the advantage of having deep spectra is you can look for abundances and have better constraints on the abundances, and we find that there's still no substantial abundance enhancement as of 2018. which sadly says that there's not, we haven't really found significant ejector contributions as of 2018. To quantify the changing electron densities that the shock is encountering, we present the evolution of the emission measure between our epochs from 2004 to 2018. And if we assume a CSM profile of r to the power alpha, which is a simple, very simple toy model, and we try to fit it with some sort of a power law, and assume, because we know the geometry of 87A, the equatorial ring, to be torus-like based on Hubble images, we can use a disk-like geometry with a volume h times the outer radius square minus inner radius square, essentially making volume here proportional to r squared. And then we can write the emission measure as a power of time. So because we have variation in the emission measure over time, we can compare the indices and see that between 2004 and 11, while the value was somewhere around 1.4, there has been a drastic decrease since then from 2011 to 2018, where it has gone to r to the power minus 2.2. And such CSM profile is again consistent with that of standard stellar winds beyond the inner ring. So this, while it's a very, very simple toy model, can't deny that the data points between 2004 and 11 show a trend, and the trend has somehow changed. And the best explanation is the blast wave interacting with less dense CSM. So going back to the monitoring observations, we also have, along with rating spectra, we have CCD spectra, which we obtain once every 6 months. These were also fit with two-component plane parallel shock models. But now we fix the abundances to the values that we got, the much better constrained values that we got from the grating spectra. And tying back to one of the previous talks, hard X-ray continuum between 10 and 20 keV was detected in New Star and was suggested to be from a pulsar wave nebula. But contribution of such a heavily absorbed non-thermal component is pretty negligible in 0.5 to 8 keV, and we do not need a third component to fit the spectrum in our broadband. So here I present the latest X-ray light curve from Chandra, and I present 0.5 to 2 keV light curve and the 3 to 8 keV light curve. And this light curve has been built up on several years of work. So just to give a quick overview. So there was a dramatic flux increase since 2004 when the blast wave started interacting with the main body of the equatorial ring. Since 2007, this increase rate changed from exponential to linear as optical and mid-infrared emission started to fade off. And since 2013, we saw that the X-ray flux leveled off up to about 2015. So that was where I took over from Frank et al. For in this measurement, and we noted some sort of scatter between 2015 and 2018, which is exactly when all these other works have reported the blast wave moving out of the equatorial ring. And since 2018, there is a systematic decline in the X-ray light curve, and this was also seen in concurrent XMM and E Rosita observations. And an important point to note here is because ACES is affected by the OBF contamination, we have to be very careful about whether it's an actual decrease or it's because of the changing contamination. To avoid that, we also have the HRC measurements here in green, and they are not affected by the contamination, but even they are declining. So that's a strong indication that this is somewhere where the turning point is for 87A, where the blast wave has left the equatorial ring. So the 0.52 keV soft light curve is more sensitive to density changes, while the hard X-ray light curve has been increasing across all these phase transitions linearly about 10% per year. And they are thought to be from low density CSM within the equatorial ring, and they could also be possibly material from outside the equatorial plane, so above and below the plane. So we also compare our latest light curve with the latest magnetohydrodynamic model, assuming a blue supergiant progenitor. So we find that the model predicted fluxes are generally consistent with observed fluxes. So this is from Orlando 2020, B18.3 progenitor model. And we see that the most important, the selling point of this plot is that somewhere around here, the model predicts that the ejector contribution overtakes the ring contribution. And that would mean that while we still have not seen strong ejector, metal-rich ejector contributions, right now we are at the cusp of this turning over point, and it will be very interesting to see if 87A finally goes from a CSM shocked supernova remnant to an ejector-dominated supernova remnant, and upcoming observations would be crucial to constrain such contributions. So now coming back to the main strength of Chandra, which is spatially resolving the remnant of 87A. So we have several images between 1999 and 2021. I'm just showing some of them as a representative here. And one way to track the morphology changes in this remnant is to measure the expansion rate of the radius of the ring. And to do that, we define the peak radius as we estimate the center of the remnant and then estimate the distance from the center to peak X-ray emission inside the equatorial ring and take an average of all the lobes. So we assume it's a simplification, but we assume 4 lobes plus a torus model, which has also been used in previous works. And we continue the measurements that have been previously done. So the radial expansion clearly shows that around 6,000 or 2004, the velocity, the fast shock velocity is hit by the equatorial ring, and it changes from about 6,500 to 1,500. However, the crucial information here, even with the latest data, if we expect the blast wave is interacting with CSM of lesser density, we should expect faster shock velocities rather than continue on this path, which was previously consistent with the flat light curve. But what we think here, so this is all tentative territory because we're still working on it, but we think that while the blast wave could have started to move out of the equatorial ring, the peak X-ray emission could still be within the ring. And because of that, our simple model still considers the evolution of the peak radius from within the ring. So to combat this, we slightly modify our model to measure the outer boundary of the blast wave rather than the peak emission of X-rays. And from that, this is a very tentative plot, but since 2016, we see this change in the slope of the velocity compared to the rate that we would have expected if the shock was all within the equatorial ring. So this sort of expansion is consistent with the shock interacting with less than CSM outside the equatorial ring. So again, future observations, if they continue this trend, that would provide more truth to this argument. So the reason why this might be happening again is because one of our parameters in our fit is the thickness of the equatorial ring. And since 2016, there's like a drastic change. A big caveat, of course, is that these values are right at the edge of the Chandra resolution with after subpixel resolution and deconvolution. But if it continues, this would be very interesting to look at. So just to show some future plans that we have. So multi-cycle Chandra observations have already been approved. So till 2024, so we'll be continuing to observe and measure the light curves and look at the images and confirm a lot of the tentative trends that we see in the light curve and the radial expansion. Also, very importantly, our cycle 24 observation would also be simultaneously observed with PRISM, which has 87A as one of its priority A targets. And this is an unprecedented opportunity because you can combine the excellent spatial resolution of Chandra with the excellent non-dispersed spectral resolution of PRISM to understand any or characterize any metallic ejector contributions and also reveal the nature of the progenitor. And we are also part of the JWST near-cam observations of 87A. And this would be a continuation of our Chandra Spitzer monitoring program. And finally, as always, we continue to search for direct evidence of the compact object in Chandra images. That would be the death knell of all the arguments against and for the compact object. So I would just like to leave you with my summary slide and some of the results. It might have been already published in one of my papers. And the other one is in preparation. So if you would like to look at more details, I encourage you to read my paper. Thank you so much.
More questions? I'm always fascinated with 87A, slow, but incrementally, we're watching as things happen. I think I saw a date flash somewhere when the expectation of the reverse shock is going to hit the ejecta. Is it about 10 years from now or sooner?
No, it's supposed to be somewhere here, but it's still not. So we provide some observational constraints. It's supposed to be between 30 and 35 years since explosion, but we are right at the edge, right there.
So stay tuned.
Yeah, but observationally, there's still no ejecta contribution from the
And
Chandra
as
side.
people percolate with a question, that leads me to the next one. Okay, so you've done all this monitoring as the shock's passing through the inner ring. Okay, now probed it. Does this give us more information about how it got there to begin with? As far as, now we have good constraints on densities and, it's more about its composition. Can you tie that back more to the progenitor system?
Yes, and one of the ways to do that is here in this model, we have assumed certain progenitor properties. So if the observations match extremely well with these models, then those assumptions would make sense and we would know more about the progenitor. So
And you flashed a lot of models. So I saw Salvo's models.
this is the MHD model, and the other models that I showed were all toy models that observational models. Not these are theoretical models.
Okay. Sure, we got time for. There we go. Sal was saying, according to the model, currently the reverse shock is interacting with the outer ejector. Okay, not with ejector rich and heavy.
So with time, we should be interacting with heavy elements and seeing strong signatures in the spectrum.
Wonderful. Thank you. Okay, there's no questions. All right, thank you again. All right. And is Rebecca remote?
No,
Right there. Okay, yes.
do you want a microphone?
Yeah, sure. Sorry, is it Deising or Deising? Deising, okay. So Rebecca Deising from University of Europe, understanding the multi-wavelength emission from Supernova Remnants. And you can go back.
Okay. All right, can everyone hear me okay? Great. So good afternoon, and thank you to the organizers for having me today. My name is Rebecca Deising. I'll be talking about some work I've been doing with my advisor, Damiana Caprioli. And in particular, I want to take things back in the direction of particle acceleration. I know this session is about connecting supernova remnants to their progenitors, but I hope if you bear with me, I can make the case for why we really need to get a good handle on how particle acceleration works, including all of the microphysics, in order to properly understand the multi-wavelength emission that we observe from supernova remnants. So, and in particular, my motivation for this is if you look at the broadband spectrum, multi-wavelength emission from a typical supernova remnant, a huge amount of it is non-thermal. And so if we want to really understand the spectrum and model it properly, we need to understand the particles responsible. And so these are cosmic rays. And so I want to show you how we can model cosmic ray acceleration over the course of a full supernova remnants evolution. And in particular, to motivate why this is so important, I'm going to talk about one particular issue where we seem to have a tension between theory and observations. And by taking into account what we find from simulations, we're actually able to resolve this tension. But first, to take a step back and just refresh ourselves on the standard paradigm for shock acceleration. The basic picture here is that you have protons and electrons being accelerated, typically at the forward shock, but sometimes at the reverse shock of a supernova remnant via DSA or diffusive shock acceleration. And so in this picture, if you have a shock represented by Tycho here, expanding outward from the shock's point of view, so in the shock frame, it's going to see an upstream flow moving toward it at velocity u1. That flow is then compressed, heated, and slowed down to velocity u2 in the downstream. And so then we can characterize the shock hydrodynamics largely in terms of the compression ratio, which is just the density or equivalently the velocity ratio between down and upstream. And of course, we have that standard prediction that if you have a strong shock, R is just going to be equal to 4. If you then consider a particle that is diffusing back and forth across the shock, this particle is being scattered by magnetic perturbations in both the down and upstream. And so this means that it's going to isotropize with both the downstream and upstream respectively. And that means that from the particle's perspective, every time it crosses the shock, it's going to experience a head-on collision, or what it sees as a head-on collision, and therefore a net energy gain. And so in this way, you have an efficient acceleration mechanism. Conveniently, you also have a predictive acceleration mechanism. So the key feature of DSA is that it predicts power law distributions of particles in momentum, but if you have relativistic particles, that's a power law in energy. So you expect your flux of protons, and in most cases electrons as well, to go as e to the minus q, where q is set purely by the shock hydrodynamics, specifically that compression ratio. And so that's how you get that standard prediction that if you have a strong shock, R equals 4, you expect Q equals 2. If you then apply some nonlinear corrections to this, you can modify your spectrum a bit, and you actually make the spectrum a little bit flatter than e to the minus 2 at high energies. And so that means that we typically expect Q to be equal to 2 or less than 2. And yet, this is in conflict with observations. And so in particular, we have a variety of observations, including of supernova remnants, that are pointing to these very steep spectra, steeper than e to the minus 2. So if you look at a lot of galactic supernova remnants, their gamma ray emission is pointing toward acceleration in the 2.2 to 2.6 range for typical supernova remnants. If we look at radio supernovae, so these very young extragalactic remnants, these have very steep spectra, e to the minus 3 or so. And then finally, if you look at the population of galactic cosmic rays themselves, given what we know about cosmic ray transport through our galaxy, this requires that if supernova remnants are the source of these particles, they are injecting particles with e to the minus 2.3 to 2.4 on average. So intriguingly, recent kinetic simulations performed by Hegarty and Caprioli were actually finding the same thing. They were getting steep spectra as well, much steeper than the nonlinear DSA prediction, which is the dashed lines on this figure up here. As you can see, as a function of time, those are those colored spectra, they're getting something much steeper. And at the same time, they were also observing enhanced compression ratios larger than 4. Now, if you recall that first equation that I showed you where we relate the compression ratio to Q, that's actually counter to what we would expect. So if you look at that relationship, a higher compression ratio gives you flatter spectra and vice versa. So this is kind of a strange combination. And so we took a closer look at these simulations, and it turns out what was happening is something that we dub the post-cursor. And it's this idea that you have magnetic fluctuations that are generated in the upstream via various cosmic ray-driven instabilities. Those fluctuations retain their inertia over a non-negligible distance when they're advected into the downstream. And then that drift of magnetic fluctuations is at roughly the local Alfvén speed in simulations with respect to background plasma. And so remember, I've mentioned at the beginning of this that cosmic rays are scattering off of these magnetic perturbations, not the plasma itself. And so that means that that drift of magnetic fluctuations also corresponds to a drift in the cosmic rays. They're basically being removed from the acceleration region, which is going to result in an enhanced compression ratio, but is also going to steepen their spectra. If we want to be a little bit more quantitative about this, you can think of the post-cursor as modifying the compression ratio that particles see. So I'll call this the effective compression ratio. So cosmic rays are no longer sensitive to U1 over U2. They're sensitive to U1 over U2 plus VA2, where VA2 is the downstream Alfvén speed. And so if you have efficient cosmic ray acceleration, as you would expect in fast shocks, that means you're going to have efficient magnetic field amplification. And that means that the downstream Alfvén speed can be a sizable fraction of the downstream fluid velocity. And that means that even if your fluid compression ratio is larger than 4, you can actually have an effective R tilde compression ratio that is smaller. And that's how you get spectra that are steeper than e to the minus 2. And so if we consider this paradigm, this actually gives us a very predictive relationship between the cosmic ray acceleration efficiency, which I'm calling psi b2 on the x-axis, the magnetic pressure fraction, psi cosmic ray on the x-axis, magnetic pressure fraction, psi b2 on the y, and the slope of the spectra that we predict. And so you can, for a simple, ones on supernova remnants, simply read off what you expect your slope to be, you can see it's typically going to be steeper than e to the -2 for, a 10% acceleration efficiency in a typical magnetic pressure fraction. However, we want to be a little bit more quantitative about this. So this was a one zone simple estimate, but really you have to solve for these parameters iteratively because the slope, of course, depends on your Alfvén speed, which depends on magnetic field amplification, which depends in turn on the cosmic ray acceleration efficiency, which depends on the slope. So you have kind of this iterative issue. And so if you want to solve something self-consistently, we need a more robust framework. And so this is the part where I'm going to kind of advertise the framework that we have in place for doing multi-zone modeling of supernova remnants or your favorite astrophysical shock. And the basic idea here is that we calculate the cosmic ray proton spectrum by solving the Parker transport equation across the shock. And the basic idea to include the post cursor is you just say, instead of considering the fluid velocity u, you consider this u tilde, which is the velocity of magnetic scattering centers. In order to self-consistently account for things like magnetic field amplification and the effect of particle acceleration, you actually solve this in conjunction with a few other equations, and you do this iteratively. So you can start with a guess for the solution to the Parker transport equation. It's basically a cosmic ray pressure. That can go into your prescription for magnetic field amplification, which gives you a magnetic field pressure. Combine that with your cosmic ray pressure, and you enter that into your hydro equation, so your conservation equations across the shock, and suddenly you have a fluid velocity which enters back into the Parker equation. And so you basically integrate iteratively until you converge on a solution, and that can give you the instantaneous spectrum of protons accelerated at any time. And then you can actually take that, use that to estimate the electron spectrum, and even furthermore, you can take those instantaneous spectra, weight them to account for adiabatic, and in the case of electrons, synchrotron losses, and add them together to get the cumulative particle distribution you expect at any point in a shock's evolution. I'll take a quick moment to mention what we're doing for magnetic field amplification, since this is actually quite crucial to the post cursor, which is, of course, driven by magnetic field amplification. And we actually do something that is tuned based on results from kinetic simulations. And we basically say that we are saturating two different instabilities. One is the resonant and the other is the non-resonant or Bell instability. For fast shocks, I will mention that the Bell instability is the dominant one. And the important thing to keep in mind there is it actually scales with the shock velocity. And so that means that if you have a faster shock, you expect more magnetic field amplification, a faster Alfvén speed in the downstream, and therefore a stronger post cursor and steeper spectra. And so in this way, we have this prediction that faster shocks should be steeper. And so to kind of actually finally show you a spectrum that we get out of craft, this is a proton spectrum for a Tycho-like supernova remnant. The key difference here being we actually evolved it out all the way to the end of its lifetime at 100,000 years or so, just to see what we would finally inject into the ISM. That's the black line. You can see we get steep spectra, e to the -2.2 or so, but it was actually even steeper in the past if you look at these colored lines, which are their contributions to that final spectrum. So at earlier times, we had steeper spectra because the shock was moving faster. And so you can get something that's more like 2.3, 2.4 at an age of 400 years, the current age of Tycho, consistent with observations. We can also take this a step further and compare to a variety of observations of galactic supernova remnants. So here I basically did a little parameter sweep of different toy model supernova remnants over typical parameters that we expect within our galaxy. And so that's what those dotted and dashed lines are. And then we predict the slope of the spectrum as a function of shock age. And then you can overlay that with actual observational results inferred from real supernova remnants. And you can see we cover the same parameter space. There is pretty good agreement here. Furthermore, we can try to see if we can get those really steep spectra that you see in radio supernovae. So here you're looking at young, very fast remnants. These things are expanding into wind profiles. Typically, they're a little bit messier, but we can make a toy model with such a fast shock velocity and see what happens. And the answer is you do get e to the -3. Note that here I'm plotting e cubed dNdE to show you just how fast or how steep the spectrum really is. So we're able to kind of span this broad range of supernova remnants. And we even have another little hint that this post cursor is real in the form of supernova 1006. So there's a recent paper out where you use the X-ray observations to estimate the compression ratio at different points around the supernova remnant. And so you can look at the quasi-parallel regions, which are the regions in which the background magnetic field is parallel to the shock normal. And in those regions, we, from simulations, expect particle acceleration to be efficient. And in those regions, we also see these heavily modified compression ratios are roughly 7. But in the regions where particle acceleration is expected to be inefficient, the quasi-perpendicular regions, you retain that standard prediction of R equals 4. Another little hint that there's something interesting going on with the presence of accelerated particles. And then finally, we can actually take this formalism and apply it to a whole host of other shocks. Choose your favorite one. I don't have time to get into all of these today, but feel free to ask me about them after my talk. We can model simultaneously the X-ray and radio emission from supernova 2004C, an example of a radio supernova. I'm working on understanding the gamma ray emission from the recent nova outburst of RS Ophiuchi. And then finally, we can even apply this to really large scale shocks. So the winds driven by AGN, also known as ultrafast outflows. So feel free to ask me about any of these after the talk. I'll simply summarize by saying that we model cosmic ray acceleration in supernova remnants and other shocks while self-consistently accounting for microphysical effects, including things like magnetic field amplification, but importantly, including the post-cursor. And this post-cursor can substantially alter your supernova remnants multi-wavelength emission in the fact that it can steepen your spectra quite a bit. If we include this post-cursor, we have a model that is able to reproduce both the steep spectra in galactic supernova remnants, the very steep spectra in radio supernovae, and finally, a host of other astrophysical shocks. Thank you very much for your time.
Thank you very much, Rebecca. And we are open to take questions. Oh, hiding up there in that. We'll start with John and then back.
Is the energy density of the alchemy wave large enough to give you a substantial velocity augment of the post-shock ions?
That's a great question. So the energy density in the Alfvén waves, I would imagine it might. What observational signatures would you expect to see from that?
The H alpha line width and the ion line widths like 6, 4.
Yeah, and naively I would expect so, simply because the energy density in the Alfvén waves is comparable to the energy density in the cosmic rays. So if that's enough to give you significant broadening, then yes. Naively, that's a really interesting thing to look into.
I was just pointing out that John had a question.
Okay, and Renault Hugh. Oh, yes.
Did you have a question?
No, I was
pointing out too.
Now it comes back to me. All right, without further ado, thank you again,
Thank you.
Rebecca. And that ends the session for today. And I guess it's lunch. We go for our own interest for lunch. Any announcements from? No? Okay, and so we reconvene at 2 o'clock.